Okay, Aztec scholars, it's Miss Berger again. Hope you guys are doing okay in this winter storm we just had round 2 of, or round 3. I don't even know what round we're on, but a lot of cold stuff outside. Hope you guys are still doing okay. I know it's caused a lot of problems for people with like pipes bursting and things like that. So it is my understanding the Aztec offices will be open tomorrow. So if you need anything, make sure to call them. Remember, they've got the food pantry and things like that. So give them a call if you need something. We are still doing distance learning because I don't know about you, but I can't really get out of my house right now. So here's another pre-recorded lecture for you guys. There'll be some questions as we go through. Kind of think about those as we go through. Don't just sit there and like stare blankly at the screen. Try to think about them. And I'll be posting a checkpoint for you guys to do on Monday that'll go over, or that will cover atoms and molecules, solids, liquids, and gases. And then I'm also going to post a periodic table overview. So it'll cover those things. So you will want to have these discussions in the back of your mind. And of course, I'll post the PowerPoints as well. So, all right, let's get started. All right, so states of matter. We've heard this before. Everything is either a solid, liquid, or a gas. There is a more recently proposed fourth state of matter called plasma. I'm not really going to get into that today. That is a separate type of discussion. It's still pretty new, but fundamentally there are three states of matter: solid, liquid, and gas. You know this whether you even realize you know it or not, just by interacting with the world around you. You know that the computer you're typing on is a solid. Like your fingers don't just go through it unless you're a ghost, in which case I have questions. You know the milk you have for breakfast is a liquid. It takes the shape of its container. Milk isn't always one set shape, because think about the gallon it comes in is different than the cup you put it in, so it takes the shape of its container. And of course, gas is what you're breathing in right now, oxygen. You're breathing in nitrogen, things like that. So those are all gases that are in our atmosphere, and we can't see them, but they are around us. And well, actually, on certain occasions you can see them, like when it's really cold outside. You can see the water vapor coming out of your mouth if you're standing outside. So that's an easy experiment you can do right now, because we all know it's really, really cold. And hopefully next week we'll see the light. All right. So why do we have three states of matter? That is a fundamental question. It all comes down to those atoms and molecules, which we've been talking about, being in motion. And so if these things are in motion, it's going to have a different shape. So like things that are, the atoms and molecules that are in gases move around a lot. That's why it's a gas. It doesn't take a definitive shape. Liquids, they're not as tightly bonded sometimes, and they don't move as much. That's why it's a liquid. And in a solid, they pretty much don't move at all. So that's why we get the standard solid state. This is another way to look at it is how tightly bonded or packed the molecules in that particular state are. So you can see there's a lot of different space in between the gas molecules here. And there's a little bit of space between the liquid, but obviously there's some room on some, and some there's not. So you could fit something through here. And then on the solid, like say this was like some salt or something like that. It's a solid crystalline structure. It's not moving. It's going to stay the same rigid shape, and you're not going to be able to fit anything in between the spaces. So just like if you've ever heated up a cup of water, or as you can see for examples outside, as we go through this great melting that's about to occur, if you look outside right now, there's water in multiple different states right now. It may be solid in the form of icicles hanging off your house. It may be a liquid when it starts to melt here in the coming days, once we get above freezing. Finally, whee! And if you've seen images on the news and stuff lately, you can even see water vapor coming off these big lakes and things like that. That's where it's a gaseous form. So we're experiencing all three phases or states of matter of water in this week because of the crazy weather. So we know that when you heat a solid block of ice, so it's a solid, it's water, but it's solid form, you're going to speed up the molecules. You're going to break some bonds, you're going to speed up the molecules, and that's what's going to lead it to liquid. So the molecules can move around a little bit more, there's some more kinetic energy to them. But if you heat the liquid up even more, there's even more space between the particles, the molecules. They're moving around very quickly, so that's why we get the gaseous form. And the reverse happens. So if you take water vapor gas and cool it, it'll become a liquid. And then if you cool it further, it'll become a solid. So each time we're losing space between the molecules and it's taking a more rigid structure. There's less vibration of the molecules. So you can look around wherever you're at right now. I mean, I'm not in your house or your apartment with you, but I bet you're surrounded by solid objects. You're probably sitting on a solid object, whether it's a chair, maybe you're sitting on your bed, maybe you're sitting on like a pillow fort in your living room. I don't know. You know, snow days do weird things to us. I like pillow forts personally. So remember, a solid has a definite shape and a definite form. It's not going to change. So like this sports car is not going to be a sports car today and a sports liquid tomorrow. That's not how it works. So remember, the particles are tightly packed. If you look at this example up here, remember there's no spaces between these molecules. But they're still vibrating, so you can see these little motion arrows right here. So there's still vibration, even in a solid. It's just not noticeable to the point where it's changing shape. And it's kind of crazy to think about because you're like, well, it's not vibrating. Well, actually it is. It's vibrating on the molecular level, the atomic level. And so our senses can't perceive it, but the molecules in a solid are still vibrating. So then we have liquids. So again, liquids should be pretty common to you. You should be, drinking them every day. Hopefully you're drinking water or milk or juice or something healthy like that every day. That's, it's a liquid. We put liquids into our cars to make them go vroom vroom. This is a, drawing of the atomic level of a liquid. So you can see, follow the arrows. So there's still some motion. These things are kind of falling over each other, tumbling around. The molecules don't really stay in one particular spot, but because they occupy different spaces, so to speak. So if you put this smoothie in this cup, and it looks like, it takes this shape, whatever shape you want to call that. But then if you put it into a lake where it's going to spread out more, those molecules are going to distance themselves apart from each other, and it's not going to look like a smoothie anymore. So the liquid is going to depend on what container it's in, and that's what the shape those molecules, when they're tumbling over each other, and for that kinetic energy, that's what it's going to look like. So you can see they use the term slide over one another, so that's what these arrows are showing. It has a definite volume, but not a definite shape, whereas a solid has a definite volume and a definite shape. All right, gases, the third state of matter. All right, so remember, this is where there's a lot of kinetic energy to the molecules. They just kind of bounce off everywhere. They do what they want. Gases are all around us. It can be the steam coming off of your cup of hot cocoa. It can be the steam, the water vapor coming out of your mouth when you're standing outside in the snow, if you have a snowball fight with your siblings. It can be the air in the balloons at your cousin's birthday party. It's the atmosphere. It is just, there's a lot of different gases in our world. So the key thing about here is they have no definite volume and they have no definite shape. So there's going to be comparisons between all three states of matter like that because of how they either do or do not take their shape, or how do they fill a container. So just like liquids, they take the shape of their container. So if you, it's like a balloon is a great example. We have filled this balloon with our breath or helium or whatever it is, and it's taking the shape of that balloon. If it was not in the balloon, it would just be floating about in the air around us, and we wouldn't be able to definitively say where that particular bunch of gas was because we can't see it. But if once we put it in the balloon, cover it with a yellow plastic container, we can go, this bunch of gas is right here, and I know because I put it in this balloon and it filled the shape of the balloon. So, and a gas, just like in this picture, you can see the particles, the molecules, they're kind of everywhere. They're kind of like bouncy balls. They're just going all over the place. You can't really contain them. They have a lot of kinetic energy. So it's very free moving, basically. All right, so we know just from looking at the example of water, like this is all of Oklahoma right now. Oklahoma and Texas where it's like, what happened? We know just by looking at the current state of the weather that things can go through different changes of state. So, you know, water can be ice, it can be a liquid water, or it can be water vapor, the gas. But it's all water. It's all the same molecule. The molecule structure does not change when we go through different changes of state. It just depends on the amount of kinetic energy or the number of bonds. So different things can cause these changes in state. Usually it's adding or removing thermal energy, so heat. So adding heat or removing heat. That's what that's saying. So there's a couple of different terms we use when we're going through phase changes. So if we're going from like a solid ice to a liquid ice, we all know that means the ice is melting, right? And say you put some liquid water in your ice cube tray in your freezer and you want it to become solid ice. Well, we know that's called freezing. That's why the freezer gets its name. These are not new terms. So when we're freezing something, the heat is leaving the liquid. When we're heating something up, the heat is going into whatever we're heating up. So in this case, it's going into the solid ice to melt it into a liquid ice. That's how we get melting. So that's just, these are pretty much intuitive things. I would think we use these terms all the time in our common language. It's nothing I'm sure you haven't heard of before. On the flip side, there are other phase changes that you may not use as commonly, and that's totally cool. So we're going to go over those right now. So if we're going from a liquid phase to a gas phase, this is called vaporization, or that's the main term. So this will, to get to this state, we can use boiling. It can be evaporation, like on a hot summer's day. You know, like the morning dew will evaporate off the leaves. Or if you want to boil some water, you're going to turn some of that water into a gaseous form. So this is called vaporization. Now, if you go from a gas to a liquid, so we're condensing the liquid back, or the gas to a liquid. It's called condensation. Typically you have to cool the gas to make this happen in most cases. So we're removing the heat. We're adding heat, we're removing the heat basically. We're cooling it down and it condenses from a gas to a liquid. And then this is the one that is probably a new term. Even I was, once I was working in a lab, I used the term incorrectly and I was like, whoops, my bad. So if we're going from a solid to a gas, this does not happen very often, but I bet you've seen an example of it. If you've ever seen frozen carbon dioxide, AKA dry ice, that is what's happening here. There's a process called sublimation. So sublimation is where we take the solid dry ice, it's literally solid, you can pick it up, it has a definitive shape, and it's going straight from a solid to a gas. It is skipping the liquid phase. This is called sublimation. So heat is being added to the solid and the gas is coming off of it. A lot of times people will do this around Halloween. It makes a cool foggy effect and stuff like that. This right here is just an example of what they do here is it's just colored water and they add the dry ice to it. And this is the sublimation happening. This is the solid dry ice going to a gas. Right here, you can see the gas coming off. So in this case, you can see this gas because of how dense it is. But this is right here is a perfect example of sublimation. And so again, if you've been around Halloween, anything, you know, this is a trick people use with the punch bowls at Halloween get-togethers. If you put some solid dry ice into a punch bowl, it'll sublimate off and make the punch bowl look all spooky. You know, it's cool. And also because it's carbon dioxide, like we talked about, it adds a little bit of carbonation. Remember that word? It adds some carbonation, some jazz to your punch. So here is a diagram that kind of summarizes everything I just talked about. So you can see how if we go increase the temperature, this is what happens versus how much heat energy is increasing. So that at the highest temperatures with the most heat energy, it's going to be a gas. The lowest temperatures with the lowest heat energy, it's a solid. And of course, in between, we've got liquid. So if you want to go from a liquid to a gas, you're adding heat. That's what this red arrow means. So it's called vaporization, or vaporizing. And the blue arrow means we're taking away heat. So it's getting colder. So we're condensing from a gas to a liquid. We're removing the heat. And you can see the exact opposite is happening down here with freezing and melting. which are, again, terms we should know quite well. So we talked about those molecules that make up these states of matter, the solid, liquids, and gases. Remember, the particles or the molecules will slow down as you're going from like a gas to a solid. The molecules are slowing down. But if you go the other way, the molecules are speeding up. So I already kind of talked about this, but so basically, if you're adding energy, it's going to go one way. If you're subtracting energy, it's going to go the other. So this is how we can consider it like an attraction between the molecules, basically. So here's some examples. We all hopefully have seen a hot air balloon or something like that. They're pretty cool. So to get a hot air balloon to go up, you have to heat up the inside. And that makes it warmer than the exterior atmosphere. So that causes a change in temperature, and that allows this balloon to float. So when we heat a gas inside a balloon, we're moving the particles, the molecules in here are going faster. And this results in a higher pressure inside the balloon than outside the balloon. So it's another factor. So it's a pressure difference and a temperature difference that allows this balloon to go up and expand in size. If you've never had the pleasure of seeing a hot air balloon, you should totally try to find one. They're really cool. If you ever do get to go up in a hot air balloon, I will say it is very cold because you are in that basket down below where you are not near the hot water, or not the hot water, the hot gas. And so it's rather chilly up there. But it's really cool. They're cool to look at. What, Tut? Tut says hello. He thinks he's mistreated. All right, so the opposite. So like this is a sad little birthday balloon. We've probably seen this happen before. So if you have a birthday party and, you know, our garage in our house usually gets colder than the rest of the house because most of us don't heat our garages. So that gas, kinetic energy inside the balloon, those molecules are bouncing around having a good time. But then you put that balloon in the cold garage overnight, and suddenly those molecules are not bouncing around as much. They have less kinetic energy. They're condensing down. So they're going to occupy less space. And when that happens, we get the sad little birthday balloon here because it looks all deflated because there's the same amount of gas. Excuse me. It's the same amount of gas in the balloon as when you started the day, but you put it in the cold garage so it condensed down and is taking up less space. So it's not filling the entire container of the balloon anymore. So the particles have slowed down. It's now a lower pressure inside the balloon versus the outside, and it's not occupying this entire space. So that's what happens when you get a balloon. If you're just like, man, what happened to my awesome birthday balloon? Yeah, that's kind of what happens. You know, of course, the actual term here is called contraction. You know, the balloon is contracting down, but you can also look at it that way. All right, so that is the quick review over solids, liquids, and gases. And I'm going to record one now about the periodic table, and I will post these for you as soon as I can tonight. Thank you.